All right, this is the second hour of Physics 1C for September 20th, and we're going to move straight into another example with Gauss's law. This is going to be a spherically symmetric charge distribution. All right, so this says an insulating solid sphere of radius A has a uniform volume charge density ρ and carries a total positive charge Q. So the fact that it says insulating is really important. Something you're going to have to be paying attention to as you start to see more of these problems is whether the object is a conducting object or an insulating object. This is an insulator. So an insulated solid sphere with a radius A has a uniform volume charge density ρ and carries a total positive charge capital Q. Calculate the magnitude of the electric field at a point outside the sphere, and then find the magnitude of the electric field at a point inside the sphere. So in this case, instead of talking about a point charge, what we have is an actual sphere with radius A. We're going to draw two pictures for this. So in the first picture, I'm just going to draw a sphere. It has radius A, and it carries a uniform charge density. So there's charges all throughout here. If it was a conductor, all of these charges would be on the surface, but because it's an insulator, all the charges are uniformly distributed throughout the sphere. Okay? The total charge that's contained within this is called capital Q. So that represents a sum of all the charges that are inside of our sphere. Okay? It has a charge density ρ. So ρ is we call this volume charge density, or just normal charge density. And it has, ρ is going to be equal to, in our case, capital Q divided by the volume of the sphere, which in this case, that's going to be capital Q divided by 4/3 pi times a cubed, because 4/3 pi r cubed is the volume of the sphere. Okay, so the first thing we need to do is to calculate the magnitude of the electric field at a point outside the sphere. So to do that, we're going to use Gauss's law. And the order of things that we have to do with Gauss's law, our first thing we need to do is we need to draw electric field lines. So let's do that. Let's draw some electric field lines. I'm just going to draw 6 because I don't really need to go too crazy on this. Wait, that's only 5. No, it's 6. If I'm only going to draw 6, I have to kind of spread them out a little better. Maybe something like that. Okay, so those were electric field lines. Label those with E. Yeah, so an insulator doesn't hold in electric fields, Patrick. It just slows down the ability for electrons to move around inside of it. But an insulating object that's charged, it's still going to create electric fields, because the electric field isn't like a fluid to be let out. It just says, if I take another positive charge Q and I put it right here, the electric field asks the question, what direction would the force be and how big would it be, right? And I know that if I place an object here, it's going to have a force that points this way. And that's going to happen whether this object here is conductor or an insulator. It's charged, right? It has a net charge, so there's going to be a force that's felt over here. Does that answer your question? Okay. All right, so calculate the electric field at a point outside the sphere. So step 1 was to draw electric field lines. We've done that. You can draw more, you can draw less, doesn't really matter. Just got to draw some. Step 2 is to choose a Gaussian surface such that the surface is parallel or perpendicular to the field lines. Now, this picture is two-dimensional. In reality, the field lines also come out of the page. They go into the page, left, right. There's more field lines than I'm drawing here, right? They come out radially away from the object. So what kind of Gaussian surface would I want to use in this case? Do I want to use like a square, a circle, a triangle, something else, a diamond? What do we want to use? A sphere, yeah. So we're going to surround our entire system with a sphere. Now, one thing about this to keep in mind is when I want to find the electric field at a point outside the sphere, I need to draw my Gaussian surface outside the sphere. Is that obvious? I don't know if it's obvious. In order to find the electric field at a point outside the sphere, my Gaussian surface has to be outside the sphere. Okay. Let's label something about our Gaussian surface. Let's say that our Gaussian surface has a radius that we call little r, indicated by that line right there. So there's our Gaussian surface. The next thing to do is to come along to the surface itself and draw some vectors to represent the dA vectors. So first I would say if I come to this point right here, my dA is going to point perpendicularly away from the surface, and it's going to be parallel to the electric field. And that's going to be true at every point here. If I draw my dA here, it's also going to be parallel to the electric field vector. Okay, that's really good. It looks like E and dA are parallel at all points. Next thing to do is to apply Gauss's law. So on the left-hand side of my equation, I can say that E dot dA can be simplified. This is where I'm going to start skipping steps as I do this. I know that the angle between E and dA is 0, which means E dot dA is going to be E dA cosine 0, or simplifying that further is just going to be E times dA. You can go from here to here because the angle between E and dA is 0. On the right-hand side, we can ask how much charge is actually enclosed by our Gaussian surface. How much of the total charge of the sphere is inside the Gaussian surface? Half of it, some of it, all of it, none of it? How much of the charge is actually inside the Gaussian surface? All of it, right? Our Gaussian surface contains all of the charge associated with the object. So my Q enclosed in this case is just capital Q. Because, again, going back to the problem, total positive charge Q. So big Q. Next thing we can do, just like we could in the previous problem, we can say at all points along my sphere, because I chose a sphere, as long as they are the same distance away, as long as this distance is r in all cases, and it is, that is to say we have to put the center of the spherical charge at the center of our Gaussian surface. If we did that, then the electric field should be the same at every single point on the surface, which means that we can pull the electric field out of our calculation. Right-hand side, nothing new is happening. We're already done with the right-hand side. And then all we have to do now is say this, sum up all the surface elements, dA, of our object. That's going to give us the surface area of the Gaussian, which is 4 pi times r squared. And that's equal to capital Q over epsilon naught, which means that the electric field is going to be equal to Q over 4 pi epsilon naught 4 pi epsilon naught r squared. This is for r greater than a. So something that comes out of this derivation that's really important is, even though I have all of the charge smeared out over the volume of a sphere, it's all spread out inside of there, right? The electric field that we get is the same as the electric field you would have gotten for a point charge. But it only works for r greater than a. We have not found what the size of the electric field is inside the sphere yet. That's what we'll do next. Okay, did that derivation make sense? Anyone have any questions? So one thing that you can do by looking at this equation right here is you can answer a question that someone had asked early in the class, or maybe I asked the question to you all, which was, when we think about the electric field created by a point charge, or as we see now, also by a sphere of charge, we see that the result that we get is 1 over r squared. And the question was, why is it r squared and not like r, or why is the r not the numerator, right? If you look at this line, you can see where that r squared really comes from. It comes from the fact that the surface area of a sphere is 4 pi r squared. And the size of the electric field gets weaker and weaker as you get to larger and larger sizes, because the flux has to spread itself out over a bigger area. But that 4 pi r squared shows up immediately down here, showing you that the electric field gets weaker as 1 over r squared, because mostly, we live in a 3-dimensional universe, and the surface of a sphere has 2 dimensions. And the electric field has to get kind of spread out over all that. Okay, so part B. Find the magnitude of the electric field at a point inside the sphere. Okay. If we want to go inside the sphere, we're going to zoom in on this. Make it a little bigger. There we go. So now we have this. It's the same object. I've just zoomed in because now what we're interested in figuring out is the electric field inside of the sphere itself. Right? We want to know what is the electric field inside the sphere. So that's the center. We need to draw electric field lines, but it's very difficult to do until we actually draw the object. So I'm going to go on here and we're going to skip a step, and we're first going to draw our Gaussian surface. Would you all agree that we're again probably going to use a Gaussian surface that is there we go. We're going to use a Gaussian surface that's a sphere again. Would you all agree? Probably. This one's a little bit different, but same idea, really. Let's plop it in there. Looks good. Okay, so again, I'm going to label this is my Gaussian surface. It's a sphere. Now I'm going to draw my field lines. What did I use before? Purple? So we're going to use purple to draw field lines. And again, we'll draw like 6 of them. So we'll be one kind of going this way. I'm going to draw these all out and we can talk about them. I don't think this part's obvious at all. Here's our field lines coming out of our Gaussian surface. I should really be drawing them. This is fine. Something like that. Draw one down here at the bottom. One up here. Pictures are kind of running into each other, but I think that's okay. So those are our electric field lines. Now, maybe that's not so obvious. Maybe a lot of you are sitting there and you're thinking, how do I know that the electric field lines are going to look like this? And that, this region out here that's positive isn't going to create electric field lines that maybe point in or do something else? And what I would say is that these electric field lines have to be continuous. So I drew them just to the surface here, but the reality is that if you take any of these electric field lines, they basically have to continue all the way back to the center of your object here. Like this. This. Like this. I drew them on the surface just because it just felt like an easier thing to do, but the reality is these field lines have to basically go all the way to the center of the object. Because it can't be the case that there's no electric field inside of here. So really you should be doing the same thing here. And hopefully that makes it make some sense why the field lines point the way that they're doing, but still radially away. Alright, So we've got our electric field lines, we've got our Gaussian surface, this green surface here. So the next thing we need to do is to label the direction of the area vector. And I would say that the area vector is going to point, away from, oh, come on. I just want to be able to, it doesn't matter. I'm going to say the area vector is going to kind of point in this direction. Sorry, I draw it in the wrong place. The area vector should be down here at the Gaussian surface. Draw it off to the side a little bit. So that's going to be the direction of our area vector, dA. The electric field is pointing, obviously, in this direction here at the surface, so that's our electric field vector. So we can see that they're parallel to each other again, and that's going to be true everywhere on the surface, that the electric field and the area vector are going to be perpendicular to each other. So when we go to write down, this is part B, when we go to write down what Gauss's law says, oh, I need to do one other thing here. Let's label that this distance is r. So the radius of my Gaussian surface is r. And now let's go through our derivation again. Very similar process. E and dA are parallel to each other, so we can write this as EdA. The electric field should be the same at all points along our sphere, so we can pull that out. We end up doing the surface integral of dA, which is going to give us another 4 pi r squared. So nothing changed on the left-hand side. The only difference is that the r is now different. It's smaller. We're now inside the sphere. Next, we need to deal with the harder part of this, which is the charge enclosed. So now what we have to figure out is how much charge is there actually enclosed by my Gaussian surface here, right? So I've got this Gaussian surface, and it fills in this region. I need to know exactly how much charge is there that's actually enclosed by my Gaussian, right? That's what we need to figure out. How much charge is there here? Would you all agree that it's less than capital Q? Yeah, it's less, right? How much less? How can we figure out how much less? Because we need to know exactly how much charge is inside of there. So what would we use? What we know is that the volume charge density is constant, right? Do some dividing. A minus R. I don't think it's that simple. Rho times the volume. That'll work for sure, right? So if I take the volume here, right? If I take rho, and I multiply by the volume of the Gaussian, that should work, right? Because rho is density, charge per unit volume. The volume of my Gaussian would be 4 over 3 pi r cubed. There we go. We even know what rho is. From above, we know that rho was equal to this, q over 4/3 pi a cubed. So let's copy that and plug that in here. Come on, just click here. It's so stupid. All right, whatever. So we bring this down here, that's what rho is. And then we just have to multiply that times 4 over 3 pi r cubed. And now we can kind of see that it's a fraction of the volume that's showing up here, right? The total volume was 4/3 pi a cubed, and did I just replace Q? Well, so what we did was we said Q enclosed was equal to rho times the volume of the Gaussian, right? And then I replaced rho, so rho is this. Charge divided by total volume. Okay. Now what we can do is we can do some simplifications. The 4/3 cancel out, the pi's cancel out, and what we have is Q over a cubed epsilon naught times r cubed. And on the left-hand side, this just carries down. We have e times 4 pi r squared, which we then, in order to solve for e, need to move to the left-hand side. So what we're going to be left with is that e is equal to q over 4 pi a cubed epsilon naught. And now r squared and r cubed we're left with just 1r. And this is going to work for r greater than, nope, r less than a. You can check, but you'll get the exact same answer at the boundary. So this is what we got here. Let's put both equations together here. See, why does that work sometimes and it doesn't? I don't understand. So if you check, when you put r equal to a, right, you get the same answer. So they match at the boundary, which is always an important thing to happen in situations like this. But this is our full answer for the electric fields. You've got the inside and the outside, right? And that's your solution. And we can plot it. If we go here and we put some axes in, then we can plot exactly what this looks like. So what we have is, if we plot the electric fields as a function of radius, and I indicate right here that this is the place where r is equal to a, then I would say that this is what it's going to look like. It's going to be a straight line until you get to a, because if you look at this equation right here, assuming that a is a constant and q is a constant, r is the only variable, which means e is proportional to r, which means it's going to be a straight line, and then this is the slope, basically. This little piece right here would be the slope of the line. And then once we get to a, r greater than a, it's going to asymptotically fall off and approach 0. Not really drawn to scale, but this is in general what the picture of the electric field as a function of radius is for a solid insulating object like this. Anyone have any questions? Can you explain why we got rho v Gaussian? Is it because we want what's in? Yes, that's exactly right. Yep. So Q enclosed says to take up the total of the charge that's inside of the Gaussian. The best way to do that is to take the charge density and just multiply by the volume of the Gaussian. That tells you. You put it very well. That's right, Ange. Yeah. Why we got r squared when a is cubed? Right here? Or here? Well, it's from this line. So if you look through the math, on the left-hand side, what happened was we ended up with a 4 pi r squared from doing the integral, right? On the right-hand side, we ended up with 4/3 pi r cubed. Oh, from here to here? Well, these are different solutions. This is for r greater than a, and this is for r less than a. There's two different solutions. Does that make sense? Yeah. What I did was I just copied the solution from above, so we could look at both of them, and so you can kind of see that if you plug r equal to a, you get the same answer. Now, you're going to see problems on your homework, specifically your lab manual homework, where you have a very similar scenario where you have a charged sphere with one difference, and I'm going to tell you what you need to do. The only difference on the lab manual homework is that you're going to have your rho is going to be a variable, okay? So just as a hint for the homework, so you're going to have a problem on the lab manual, I believe, where you have, is it a, yeah, well, I'll answer that question next, okay, Tom Bleed? If it's a conducting sphere, we'll answer that question next. You have a lab manual problem where, is it hollow sphere? I need to get my lab manual checked. Is it a hollow sphere that you all have? Or is it just that the density is a, let me see. Can't remember which one I assigned to you. There's different ones in there. Yeah. So the problem that this is related to is problem 275. In this problem, you have a non-conducting cylinder, okay, that's insulating. It has a radius of b. Ah, dang it, that's the wrong one. That's the wrong one. That's a cylinder problem. Where is the spherical problem? Did I not give you one with a sphere? I'm losing my mind. Maybe it's not on your homework. Maybe it's not labbing no homework. Maybe it was yeah, it's on Pearson, right? Is that what it is on Pearson? So you've got something like this where you have a sphere and they tell you that the density is going to be something like, it's a hollow sphere. Okay, so we're going to look at a hollow sphere problem later. I don't know if we have time to get to that. I hope we do. But so this is all I'm going to say. You have a problem. It's actually not a sphere, but it's really the same concept. The problem that you have is you have a cylinder. Okay, and the radius of the cylinder is b, and you're told that the density of your cylinder is rho naught r squared over b squared. So what I'm going to tell you now is that in order to do problems like this, when you do Q enclosed, okay, you're basically going to be drawing a Gaussian surface. What I'm telling you right now might not be very useful to you now, but maybe you come back and look at this when you're doing the problem, okay? I'm just going to put it up here. If you don't know what I'm talking about, that's fine. When you actually take the time to think about the problem, yeah. Your charge enclosed now is just going to be the charge that's enclosed inside of here. And to get it, you're going to have to do this. And I'll let you figure out how to go about doing that. To find your dV, you have to basically think about the volume of like a thin strip inside of here. I think about it like a piece of toilet paper. This is the part you're going to have to figure out yourself. I'll help you with it. I know what the answer is. I want you to think about it and figure it out yourself. But Q enclosed, when you have a non-uniform distribution, you have to do this. If you have a uniform distribution, that's where you can do what we did here. If your rho is a constant, you can always say that charge enclosed is just rho times the volume of the Gaussian. If your rho is not a constant, you have to do an integral to figure out what charge enclosed is. Okay? Something to think about as you're doing your homework in case you get confused. So the next question was, what's the difference if the question is a conducting sphere? Okay. Here in a few minutes, we're going to go through the details of what a conducting sphere does, but I'll just tell you right now that if you have a conducting sphere and you place charges on it, what's going to happen is that the charges are all going to go to the surface. Okay? And one of the things that we're going to prove here in a second is that inside a conductor, when all the charges go to the surface, the electric field will always be zero. Some of you that have done the lab in class last week saw this when you had a ring and you measured the electric potential inside the ring and you found it was the same everywhere. The only way that the electric potential can be the same everywhere is if the electric field is zero. Now, we haven't learned what electric potential is. We might learn about it today, I don't know. But the point is that if it was a conductor, this is what would happen, to answer your question, Tom. And you will definitely see problems like that. We'll do a problem like that a little bit later on, okay? All right, the final one. Yeah, this is an example of a problem we can do that's going to include that. The final problem that we want to do using Gauss's law, though, actually, there's one more after this, now that I think about it. It's this one. Okay, does anyone have any questions about the last problem, though? Just going back through it here. Finding the electric fields on the inside and outside of the sphere. Any final questions about this? Okay, if not, let's go into the plane of charge. All right. We want to find the electric field due to an infinite plane of positive charge with a uniform surface charge density sigma. All right, so we want to draw a sheet. And I'm going to draw it kind of sideways. So you're going to have to imagine that this is three-dimensional. So we have a sheet. And it contains charges. They're positive charges. positive charges distributed throughout this, and it's an infinite sheet, so it continues infinitely this way, infinitely this way, infinitely this way, and infinitely this way, so we're really only looking at a portion of it, but it's a sheet and it carries infinite amounts of charge. Now, in order to solve these problems, the first step was to do what? Can anyone remind me so I don't have to go back and see what it is? What's the first step that I need to use to solve a problem like this? Draw the field lines. That is correct. So let's do that. Let's go over here, go to purple. So we actually kind of already did a problem like this, right? So we kind of already know that the field lines for this type of scenario are going to look something like this. Something like that. Why can't I just control select these? I don't understand. It seems like that should be something you can do. Seems like that should be something you can do, but I guess you can't. So, whatever. Can do this, though. And we can go like this. And then just, let's see, copy, paste. Just go like that. Okay, so those are our electric field lines. And we fit them right in like that, right? That's on top. On bottom, it's the same idea. There has got to be a way to rotate. Rotate, flip vertical, right? There we go. And then we need to flip horizontal too, I think. That should work, right? Okay, on the bottom, our electric field lines look something like this. It looks kind of bad, doesn't it? Yeah, let me just draw them from the bottom. Alright, so on bottom, our electric field lines are going to point down in a way like this. Kind of draw it so that like you can't see the ones coming out from the bottom or something. Something like that, and just repeat that. You get the idea, hopefully. So something like that. We've got electric field lines. They're extending out like this. On the top they go up. On the bottom they go down. They should be evenly spaced. I apologize. I'm not going to keep drawing lines here. I hope that you all get the idea. Lines go up on top. They go down on the bottom. We now need to throw a Gaussian surface in here, and the Gaussian surface needs to be a Gaussian surface that makes it so that the surface is either perpendicular or parallel to these lines. So, and there's a lot of correct answers here. I want to type in the chat, what would be the type of shape we'd want to use for our Gaussian surface here? There are a lot of correct answers. A cube would work for sure. A cube would work for sure. Let's do that. So let's draw ourselves a cube over here to the right, and then we'll throw it onto our picture. Make it, I guess, light blue maybe? What else works? I don't know. I'll let you all figure it out yourselves. Alright, so we want to draw a cube. After I've shown you why this works, you'll be able to figure out, I think, pretty clearly what other things will work, and we'll talk about it at that time. But think about it yourself. And see if you can't figure out what other types of objects would work. Okay, so why is a cube good? Well, if I take a cube, and I stick it on here, first of all, we're just going to have a lot of other lines that are going to be kind of ugly. So let's make it really big so that it actually surrounds my system. There we go. That looks fine. Now it's very clear that some of my lines aren't straight, but that's just fine. So why is the cube good? Well, the cube is good because if I come up here, for example, and I draw my dA vector, the dA vector is going to point up. And that's going to be true really anywhere on the surface of my cube here. The dA vector will always point straight up. But our electric field lines are also pointing straight up. So that works out great. Works out great. Okay, so we're going to say that our Gaussian surface is a cube with area A on each face. So the area of the top portion here is A, the area of the bottom portion here is A, and the side portions are A as well. Okay. We can also come down here on the bottom and we can draw our dA vectors. They'll all point straight down as well, meaning that everywhere on our surface, the electric field lines, which are represented by the purple, are parallel to the dA on top and bottom, and then on the sides, they're perpendicular, right? So we'll draw one over here as an example. On this side over here, my dA would point to the right, which means the angle between the dA and the electric field line is now 90. So front, back, left, right, the angle is going to be 90. Top and bottom, the angle is going to be 0 degrees between E and dA. Okay, now that we've actually drawn it and seen why this works, is there anything I could have done with my drawing that would have also worked? Any other type of object that I could have put on here that would have also worked? A rectangular prism, exactly, so it didn't have to be a cube, right? It could have been skinnier on the sides, or it could have been wider, whatever you want. The rectangular prism would also work. Yep. Even a triangular prism would work too. A cylinder would work. Yep. A pyramid. Pyramids are kind of weird because, you know, a pyramid is shaped kind of like that, right? With the backside kind of comes down like this. I don't think a pyramid would work because it's not, yeah. But can you use the base? The base of the pyramid? The base would probably work, but the top won't work, basically. You need to have one, pretty much what has to happen is the top surface, however you shape your object, has to be flat, and your bottom surface just, you know what I mean? That's the key thing. Yeah. So it could be like a trapezoid too, right? Like the bottom surface could be like this. Actually, trapezoid won't work. You need the sides to also be, the sides have to be parallel as well. Okay, so let's go through this one. This one's pretty quick. So Gauss's law says that now that we've done all of these pieces, again, we drew the field lines, we drew the Gaussian surface, and then we indicated the direction of the electric field and the dA vectors. We did all those three things. You have to do that when you do your homework. You don't need to draw dA vectors every single place on the object, but you need to draw like one or two that are representative of the entire surface. Okay, so now we're doing this. We're going to evaluate the surface integral of E dot dA. And Gauss's law tells us that that has to be equal to the charge enclosed by our Gaussian surface divided by epsilon naught. In this case, I didn't emphasize it, but it says it has a positive uniform charge density of sigma. Okay? Just to remind you, sigma is charge over area. Okay. Alright, so in our problem, we need to do this. We've already stated that E and dA are parallel to each other, so we know that we can make the simplification that this, we can drop the vector symbols and this just becomes E times dA. Again, we can pull the electric field out here because we're pretty sure that the electric field should be the same all along the surface of our, all along the top surface and the bottom surface here. So we can pull that out. Oh, I gotta do one other thing. I realized I skipped a step that I shouldn't skip. Sorry. There are 6 total surfaces of a cube, right? 6 total sides for a cube. Sides. Surfaces. There's 6 total faces of a cube, right? So really what we need to do to solve this problem is we're going to have to find the flux through the left face plus the flux through the right face plus the flux through the top and the bottom. Need a lot more room for this. Flux through the top plus the flux through the bottom, plus the flux through what's left, front, back. That's 6, right? Yep. But which ones will be 0? And which ones will not be 0? The flux through the left, this face over here, your dA points this way, but the electric field goes this way. So the angle between E and dA is 90. So when you evaluate this, what are you going to get? When I do the left face over here, what am I going to get when I do the integral? Am I going to get e times a? I'm going to get 0. What about the right side? Right side's going to be 0. What about the top side? Not 0. Front side, 0. Back side, 0. So it's just these two that we need to do, right? It's just these two right here. So we're going to have, for this one, we can say what I said before, which is now our integral will become just EDA. Plus, the bottom, you're going to have also an EDA. And all of that's going to add up to Q enclosed. Well, again, one of the things you need to think about while we're doing this problem is what is Q enclosed going to be equal to? You'll tell me what that is here in a second. Okay, once again, we can pull the E out of here, so we're going to have two integrals. We're going to have ED, well, I'll just indicate this is top and this is bottom. So we're going to have E times the integral over the top dA plus E times the integral over the bottom surface dA is equal to charge enclosed. What's charge enclosed going to be? How much charge do we actually enclose of our object here when we cut out a sphere? How much of the charge is actually going to be in our surface here? It's going to be related to sigma. The sigma alone won't give us the answer. It's got to be sigma times an area, basically, right? It has to be sigma multiplied by some area. And it's going to be A. Because A is the area of the top surface of this cube. A is this area here, basically, right? And so that area projects down onto our surface as also the same area A down here. So if you take sigma times A, that's going to be what the charge enclosed is. So let's plug that on the right-hand side. So we have sigma A over epsilon naught. Next thing we need to do is on the left-hand side, we need to integrate over the top side dA, which means to sum up the total area of the face on the top of our cube, which is A. So we're going to have EA plus sum up the surface area of the bottom of the cube, which is also defined as A. So we have EA. So on the left-hand side, we have 2E times A. On the right-hand side, we have sigma A over epsilon naught, sorry. So the areas can all cancel out of our equation because there's an area in every single term. And what we get is 2E on the left-hand side. On the right-hand side, we just have sigma over epsilon naught. And then the final result we get by, well, I guess to keep everything nice and neat here, let's just say that this tells us that in this scenario, the electric field is equal to sigma divided by 2 epsilon naught, which is the same answer that we got in the previous chapter. But in the previous chapter, we actually had to do two different integrals to get to this answer. We had to solve for the electric field of a ring of charge, extrapolate that to the electric field of a disk of charge, and then we had to say what happens when the disk grows infinitely large. So we actually had to do two integrals and a limit in order to get to this answer that we got by, I mean, honestly, you could do this in 2 lines. Like, if you actually understand what all these steps mean here, I'm not suggesting you do this. You should show all the steps if you want full credit on these problems. The reality is, though, that everything that occurred up to this, in between here and here, you could really jump from the first line to the bottom line. Like, if you're standing at the board and you're explaining this to somebody, right? You could say, well, I'm only going to get flux on the top and the bottom, and the flux on the top is going to be E times A. The flux on the bottom is going to be E times A, right? And then you could say, how much charge is enclosed? Well, that's sigma A. So in reality, you could really skip from this first line all the way to this last line, and then do one more step of algebra to get to the answer. By comparison with doing it the hard way that we learned first, which is that you have to find there's a bunch of stuff. Basically, 2 integrals and a limit. Much, much, much more work. This is way simpler. I know that it can seem very intimidating when you're doing these kind of problems. I promise you that when you go to do your homework problems, it will be this simple for almost all of them. The largest difficulty you'll see, I believe, with Gauss's law problems is going to come when you're doing the lab manual problems. Because there will be some problems you need to do there that will be a little bit more challenging, but the concept of what you're doing, you can follow this procedure and it should help you pretty well. So that's this is a good spot to stop, because I think this class goes until, I think, 4:20 or 4:30. I think I have it up here. 4:25, okay, so this is a really good time to stop. So we'll take a break. If anybody has any questions, please feel free to ask. We'll go until 4:20 p.m. And I'll wait to see if Mr. User Account types in a question here. What? Oh, 320. 320, sorry. All right, I'm just going to stop it because, oh, here we go. You have a question with regard to the shape surrounds the fields. For the one that was in regard to the sphere, I'm having some trouble seeing how exactly the sphere around the sphere is parallel. Yeah, sure. Yeah, we can talk about that real quick. So looking at, for example, I guess this one here. So the thing you have to understand when I'm drawing these pictures, Michael, is that they're actually supposed to be three-dimensional. And I can't always do the three-dimensional parts of it, but do you understand that emanating out from this sphere in the middle, that you're going to have electric field lines that are going to be coming out, radially away from your sphere? And following up to that, do you understand that there's actually lines that are coming out of the page? Like there's a line that would come straight out at us. There's lines that kind of come out at an angle. You have to imagine like a ball. I think about this. You take like a tennis ball. If you were to poke like needles all around the tennis ball, at every place that you could find a way to put a needle in, and poke them in perpendicular everywhere, then the way that those lines come out would be what the electric field of this looks like. Does that part make sense? That you've got field lines kind of emanating everywhere? Okay. So then you have to think, to answer specifically your question, you want to answer how does the sphere around the sphere leads to parallel and perpendicular to the lines? And the answer is because you have to think of the sphere in terms of the direction that if you were to take your sphere, and it's curved, and you were to put your thumb on the surface of the sphere, and you want your thumb to be poking out of the sphere so it's perpendicular, that's how you draw the dA. And so when I say that the field lines are perpendicular to the surface, what I mean is that this line makes a right angle. In this case, it's only perpendicular, by the way, Michael. This is a right angle with the surface, right? Does that part make sense? That the electric field line makes a right angle with the surface itself. The surface is curved, but the field line comes out like this. So even though the surface is kind of curvy, you could still say that at that location that the field line comes out perpendicular to the surface. Does that part make sense? Okay. Well, that's really all there is to it. In this particular case, all of the field lines are perpendicular to the surface at every single point. There's no parallel. Okay, does that help to clarify it for you? Every field line pierces the surface, and at any point, it's at right angle to the surface itself. When you're talking about a line being perpendicular to a surface, I understand that by itself is maybe not super obvious, but that's the kind of thing that I'm thinking about. You good? Okay, good. Great. All right, good question. All right, take a break until we'll do 4:21.